Sounds good. Thanks, Ingrid. Appreciate the opportunity to be here to speak to all of you today on field and lab testing for concrete pavements. Again, Steve Walkus with the Michigan Concrete Association. I've been with the association now for 19 years. So I've been in Michigan for that long and have been in concrete and concrete pavements for my entire career. So it's kind of a passion of mine, and very happy to talk about field and lab testing. I guess we'll get right into it. This information um, is going to be applicable to concrete in general as well. So we'll talk about that in a minute. But what we're going to cover today is some of the common field and lab tests. And we'll dive into specifically on some of the fresh tests, real quickly, some of the highlights of those, and then focus primarily on strength tests, because since that is the main basis for how concrete mixtures are designed, how they are specified, and how they're typically paid for or accepted. So we'll talk about that in a little more detail than the rest. But I'd be happy to talk about any test that you know of or don't know of about concrete or concrete pavements. And I can speak to most of them, but I just picked a few to cover today, kind of the main highlight, main basic ones that we typically deal with on a daily basis. So here is the full list of all the things that at least I think of when I think of what do we test when we build things out of concrete. What are the tests that go into that, the ability to place that mixture for its intended purpose to be a strong, building material, whatever it is. Pavements obviously is kind of what we're focused on here because some of these are pavement specific. But I'll just go through these really quickly because this is the only place where I'm going to talk about all of them. But make note of this. If there are some of these that you do want me to get into and we have time at the end, I'd be happy to talk about them. So make sure you take a note of this. And this is the only slide where I'm going to have all of them listed. But we test the aggregates that go into the concrete. So concrete is a mixture of aggregates and paste, and the paste glues it together. That's the binder, and the paste is cement powder and other powders and water and possibly some chemical admixtures to do various different things. But that mixture then, chemical reaction goes off, and the cement powder and the water chemically combine, and magically, quote unquote, through the miracle of chemistry, it glues it all together, essentially, right? So, but the aggregates constitute the majority of a cubic yard of concrete, and we do a lot of testing on those. If it's a state job or any job that falls under federal highway funding, there you have to follow typically MDOT specifications, and a lot of cities and counties and other non-public agencies even reference MDOT specifications at times because they have a pre-qualified aggregate testing program where they test those aggregates. The majority of the aggregate sources in the state participate in that if they do supply any MDOT work, because it makes sense, because they can get fewer frequency of testing than if they did not participate in that pre-qualified ag source program. They test for gradation, physical properties. The sand sources require ASR tests now under MDOT specifications. So we to make sure that the sand is non-reactive with the alkalis coming from the cement. Yeah, there's a lot of testing that's done on the basic materials. Other materials, the cements themselves, and the admixtures, the chemicals, those companies that supply those products that maintain their product on the qualified products list, QPL, that MDOT maintains, they have to periodically submit samples as well, or submit test results with their materials to prove that they are still, formulated properly and working and fulfilling their intended purpose at the given manufacturer recommended dosage ranges or that type of thing. So that is periodically done as well. Every time a new mix design is created, or new job mix formula, as they like to call it, because design is different than proportioning. The job mix formula is the actual recipe, the proportions of the materials. Every time a new mix design is done, or you have to reaffirm, a mix design that you've been using because the data is out of date. I believe it's every 2 years. There's a lot of testing and trial batches and things like that are done all the time on concrete mixtures. And then once you're into a project, there is quality control testing that's done by the contractor or their supplier or a testing company that's doing it for them. consultant or materials testing firm or whatever it is to periodically test per their approved QC plan um, the fresh and hardened tests. And then the agency, the owner, typically has to do some quality assurance testing as well, periodically, so that they can their independent testing is their test results essentially are shown to then meet the specification requirements. So the fresh tests, typical ones, temperature, slump, density, and air. And then the hardened test, typically just strength is the most common. There are others that we can do on the hardened concrete as well. For opening to traffic strengths, especially for bridge decks and pavements and things like that, and even driveways, drive approaches, and things like that, they'll do flexural beams for opening to traffic only, not for pavement typically, unless it's a concrete patch job. Then the opening to traffic beams suffice for the pavement as well. As far as pavement specific tests, there are quality assurance or quality acceptance tests. Coring is typically done on concrete pavements for thickness to ensure that we have reach the design thickness in place. And then ride quality or smoothness, which is measured in IRI, International Roughness Index, the units of which are inches per mile of roughness, with a typically a lightweight inertial profiler laser, mounted on a gator or golf cart or side by side or something like that. Typically, those units are available to measure ride quality. That's typically done for higher speed facilities, usually 45 mile per hour and above, where that is a requirement for ride quality. Lower speed facilities typically don't have that type of a test being done, usually just meeting a straight edge spec. Long term, then, once the pavement, again, this one's pavement specific, once that pavement is turned over to the owner, in this case, MDOT measures them every 2 years. Every single pavement in the entire state is driven by their van, which then measures a lot of different things on on all the pavements that they have. Roughness or smoothness, if you want to look at the positive or negative aspect of that, they measure that as well long term, not only the initial ride quality as built, but then long term to put those numbers into their pavement management system. They used to measure something called distress index, which was a measure of the number of cracks and faults and raveled, joints and rutting and all the different distresses that might show up in a concrete or asphalt pavement long term. They've stopped the calculation of that and they switched to a different thing called pavement distress score. Still same type of thing, but the numbers don't directly correlate one to one. There's instead of it being built at a 0 and increasing in distresses over time, it's built at 100% condition and decreasing in number over time. But at any rate, another thing that they periodically sometimes do on concrete pavements is a falling weight deflectometer to measure the response of the concrete slab, the deflection of it underneath a given load that's applied to the pavement. So they're typically trailer mounted devices that are brought around, and then they have to stop and then do that loading. And there's sensitive measurement being done of the deflection of the slab underneath that load. And from that, they can back calculate a lot of different things, not only the concrete things, but the support layers below it. And they can back calculate some support conditions. Typically, they do this for rehab type projects or in lieu of more invasive techniques like soil borings and cores and things like that to try to figure out what the support conditions for a future work done on that section. And then troubleshooting. Sometimes we'll do some different tests. Typically, these are not MDOT approved, but we see this typically in the commercial, industrial, and other segments of the concrete industry. Two in particular, rebound hammer, or what's called Schmidt hammer, which is you drop this little device and it measures how far it bounces back, and it's a measure of the surface strength of the concrete in that location. And it can be correlated if you know enough specific things about that mix and about that concrete. It can be that amount that it rebounds back can be correlated to a particular actual strength number. And then there's one that's a little more destructive than non-destructive, which is Windsor probe, which is where you essentially take a you take a charge, a little, like you'd see a bullet casing, and then it shoots this device, this probe at the concrete, does a little bit of a damage to it, but knowing that how that responds, you can determine the concrete strength as well. We have a question here, Ingrid.
Yes. So this question is a little bit about that kind of post construction testing. So the question is this individual has a 8-inch concrete that is acting as a brick paver subbase, and they've had some sporadic kind of crumbling in the upper 2 or 3 inches. The pavement is fairly old, 20 to 30 years old. They're wondering what kind of tests might be able to tell them if how deep that damage might go, and if it would be appropriate to maybe do a mill and then bond coat and top that off versus having to replace all 8 inches. Is there anything that could kind of tell you how far that damage would extend?
Uh, the only way I would probably easily be able to figure that out is with just taking a few cores in selected locations. There's no good measurement tool that I'm aware of to determine if that top part is if it's crumbling, if to the extent of which that crumbling is occurring over the whole area, other than I guess you could take a falling weight deflectometer and see. I don't know of any specific way using that device to determine that, but um, I'm more of a practical engineer. Maybe that's what the PE after my name stands for. Where I would, knowing that, I would say, all right, well, we'd remove the brick and then remove that loose material and visually assess it and to essentially do a field engineering on the spot and figure out what to do from there. But that's hard to it's hard to estimate. I understand from an engineer's perspective, figuring out what's our cost going to be in this situation because it's going to be determined on the fly. So
Yeah, that sounds like a tough one to try
yeah.
and test your way out of.
Yes. Yep.
All right, that was the only question I think
Okay.
we've got so
Good.
far.
All right. Well, keep thinking about any of these if you do want to hear more specific on these, because I am actually going to focus primarily first off on some of the fresh tests, and we'll hit the highlights. Very common. Like these are the most common testing that we do of concrete. Obviously, we do all these to various amounts, but we're going to focus on that, the highlights of those, and then we're going to dig into specifics on the strength side, things to look for, things to remember, because, as I said, strength is used as the basis for payment or acceptance on almost every job where concrete is involved. We're measuring concrete strength. So, okay, let's talk about slump. We're picturing, have a picture of the slump test having been done and the vertical distance that cone of fresh concrete slumped once the mold was removed from its original height there. And so that is for those of you that aren't familiar and don't see it, but have heard the word, that's what's going on right there. In my opinion, there's a lot of emphasis placed on slump. It is a very old test. It's been around for 100 years-ish, plus or minus a few decades. And we do it because it's very easy to do. Historically, back in less technologically advanced times, uh, the slump test was a measure of how much water did we add to this batch versus the next one, or the next one that we test at least. Because we didn't have chemical admixtures. We didn't have, different cementitious materials to choose from. We just had what was available, which is pretty much the same thing, regular Portland cement. And we had our local aggregates, our local, whether it was crushed stone or gravel, and then local sand. And then the only quality control to check one batch versus the next, to figure out how much water do we actually add to that batch, if everything's done by hand or by estimate, as far as proportioning and mixing, was to measure the slump from batch to batch. And so that made sense. Nowadays, with the use of chemical admixtures, you can have a slump within the desired range or specified range, yet it be bad concrete. And you could have a slump that's outside of the range at which you wanted, yet it still be much better concrete. So there's a lot if everything is held constant, yes, slump can be a measure of how much additional water made it into that batch or got held out of that batch. Yes, I understand that. But if we're at our water cement ratio, and the slump is at a workable spot for the contractor, that's the most important thing in my mind. Um, is a workable mix, that the contractor can work with and achieve good consolidation and a good finish and no bug holes when the forms are removed and all these other things. That is the most important thing. And I mentioned water cement ratio. That's the biggest thing. And we've heard of projects where water's been added and mixed in after the sample was taken that was being used for these fresh tests, slump being one of them. Um, that's a no-no. Specifications typically do not allow that. Once you started placing the concrete in the forms, no additional water should be used mixed into that batch because you don't know what the water cement ratio of the actual in-place concrete is going to be then. We've heard of contractors wanting to add a lot of water to aid in finishing the surface, especially these newer mixes in the last couple of years that are more thirsty, have higher water demand, and slower bleed rates of water to the surface after it's placed. The surface looks dry, and it is dry, and they want to add water. That's good and bad. If it's water that you need it, but it's elevating the water cement ratio and weakening the surface. But if it's water that you need and that you'll have unhydrated cement because if you don't add water, then which one's worse? It's hard to know. And so curing is also way more important than slump, in my opinion. People focus too much on you can get a number out of this test method. You can't get a number out of proper curing or lack of curing and things like that. There's no test method that says green light, yellow light, red light, that type of thing. So that is, take it for what it's worth. Everybody pretty much specifies a slump plus or minus or a range or a max, and you got to hit it because it's in the specs, but it's not necessarily the most important thing. The key is to have a good workable mix for your contractor so that we can achieve the desired end result. Unit weight or density, where we literally just weigh a known volume of concrete and we get the pounds per cubic foot of that particular amount, and then that's essentially the test method, is a great process control or quality control tool for contractors or suppliers to know what their density is every time the other tests are being done. It's not required necessarily in every specification. It's not typically done as a QA or acceptance type of test method, but is a very good thing to use for quality control because it can identify changes in the mix, it can identify variability in the proportioning of a particular batch, and then is also based on if you have consistent unit weight numbers, but some of your other numbers are changing, which is the one that's the correct test. So in other words, let's say we do the density test and that's been consistent, but our air content changed in this one particular time we did the air content, but the density did not. My guess is it's probably a faulty air meter or improperly done test that particular time because the density, if it weighs the same as the previous density time you did it and the air was good on that one, that's got to be, there's something else going on. And so that's potentially a faulty air meter. What if you get a higher density? In other words, it weighs more, right? Given that same bucket, like you see pictured there, that same volume, but everything else was the same. The air content was fine and slump was fine. Maybe you've got a higher cement factor. Cement weighs over 3 times the weight of water. Typical cements are about a specific gravity of 3.1. Which is a measure of the ratio of its weight or density, I should say, versus water. So if you have higher density, but everything else is the same, maybe you have more cement in that particular batch, which makes it a heavier, and that would then can trigger a look back at batch tickets if they've got batch weights printed on the batch tickets to take a look at that. If you got a lower density, for example, it's lighter weight, right? Given that same volume with a higher slump. All right, maybe we got more water in the batch. Water, weighs 62.4 pounds per cubic foot, whereas concrete weighs about 150 pounds per cubic foot, roughly. I think as engineers, we learned that in design school as far as the good rule of thumb to use for concrete. That's, less than half of the density. Water is less than half the density of an actual concrete. So if it's got lower density and higher slump, more water in the mix, those are two keys that, again, maybe we got additional water in that particular batch. So again, it's a good quality control tool, very highly recommended. And all it requires of technicians in the field is when they're doing an air pressure meter test, that they literally, they strike it off with a plate instead of a bar, but that they also just have a scale in the field and they just weigh the bucket and then know the weight, write that down, figure out the calculations later on what the density actually is. But literally, all they have to do, if they've got the same bucket all the time, they just got to measure the weight and write down the weight and see if that weight of that known volume changes over time. So, all right, air content. Here is a pressure meter being filled here, probably on layer number 2 out of 3. Um, Air content, air bubbles, minute microscopic air bubbles, closely spaced, spread throughout the paste, the cement that's in the concrete. That is what gives us freeze thaw durability in our harsh, freeze thaw environments here in Michigan. The problem is the less water you have, it's harder to get a good air void system. So low slump, low water cement ratio, just very little water in general in a mix, because the water with the air entrainment admixture, think of that as Dawn dish soap or your favorite brand, whatever it is, of dish soap, Costco brand in my house. That when you take dish soap and you put some on your hands and you rub them together and your hands are dry, they're just slimy. But as soon as you put some water on your hands with that surfactant, which is what dish soap is, which is what air entrainment admixture is, and you put water with it, now you get bubbles. Now you get foam. So you need the air entrainment admixture, you need water, and you need mixing. Those 3 things is what creates the microscopic air bubbles. Well, if you have the air entrainment admixture in the mix, but you don't have a lot of water, and then you have the mixing going on, you add water on site and remix it 30 revolutions into a ready mix truck, you'll actually be creating air. Not only you're increasing the slump by adding water to that batch, but you're also going to be increasing the air because the chemical's already in there. So that's a good thing to remember. If you're adjusting water contents on site, air may come along with it if it's an exterior mix that has air entrainment in it. Also know that if you start getting up above 8%, typical MDOT specs for full pay are 5.5 to 8.5. Historically, they were 5 to 8, or in the old spec books, they were written 6.5 plus or minus 1.5. But just know that there's no such thing as an 8.1 or an 8.2 per the ASTM specification. Everything above 8% based on the dial that's shown there is only read to the nearest 1/4%. So that's something else to note and have a discussion with your field techs. There's no such thing as 8.1 or 8.2. It's either 8 or 8.25. Question?
Yeah, are you familiar with the super air meter?
Yes, very familiar. We've done some certification classes for folks around the state on it. We have some here at our training center. I know MDOT owns a bunch as well. The super air meter is like what you see pictured here, except it has 6 clamps instead of 4 because it goes to higher pressures. This one goes to when you do an air pressure meter test, you're actually pressurizing it up to 14.5 psi, and then releasing that pressure to the full thing. I know the gauge doesn't show that; it just shows initial, initial pressure, and not in psi. But at any rate, the super air meter does that, and then it does it to 30 psi and then 45 psi, and then you release it back down and you do it again, and you measure the difference between those 2 curves at 14.5, 30, and 45. And it's that difference between those 2 curves that is the SAM number. It's a measurement of the stability of the air content from those 2 different cycles of doing those tests. So 3 times the pressure, 2 full cycles, so 6 pressure tests on the exact same bucket of concrete. And then that's what it does. It tells you the stability. The problem with it is that the precision and bias there's research that's been done and it's been published, I believe by AASHTO. The precision and bias is equal to the actual number you're reading. So the 0.2 psi is kind of what you want as your delta between those 2 curves. That's a good SAM number, but the precision and bias is plus or minus 0.2%. So it's a great lab-based tool, but the repeatability and reproducibility in the field and for QA and acceptance have not been proven out to be accurate enough. But if I were an admixture company developing a new air entrainment admixture, I would have one of those in my lab, and once I got my new formulation, I would want to see how stable it is over time and at these different pressures. So it's a great tool. It's just not a good QC or QA tool in the field. It's also very at those high pressures very susceptible to temperature because if you understand Stokes' law, pressure, volume, and temperature relationships, basic physics, again here, gas laws. Um, I actually took one out on a job and I was in either spring or fall, but I left it in my trunk overnight, drove up to the job site, took it out. It was still cold. Did the first test, got an error. Did the second test, got an error because as I was pumping it up, you're producing friction, which is warming it up and warming up the air in that top chamber. Whereas the rest of it, it's a metal, it's a metal meter. It's slowly starting to warm up. And same with, so for temperatures that are variable then throughout the day, throughout the night versus day, throughout a concrete mix temperature versus air temperature versus the meter temperature. It has a high variability because of that. So, but in a lab situation in room temperature, a very good tool.
Well, we're talking about field things. And also I think you probably gave people some flashbacks to freshman chemistry by mentoring Stokes' law. Um, what are some allowable actions that could be taken in the field to raise or lower air content in the event that the test comes out and says that it's out of spec?
Yep. So typically we do a slump and air check test at the beginning of the batch. So we don't get an official sample or a big enough sample to do all the cylinders and stuff at the end because that's not a proper sample. But as a check test, those are the two that we do. And if it's low on slump, we can add water and mix it in 30 revolutions if it's ready mix application, obviously. And it'll probably get some air with that. And so the same thing, if you're low on slump and air and you have room to add water, you could just add water and not add air and training admixture, and you'll probably get some more air, like I talked about. If you're good on slump, but you are low on air, you can add air and training admixture if the driver or a QC person or somebody, has the same air content or chemical air and training admixture that was used and knows how much to add based on consultation with the right people that are knowledgeable in those things. That can be mixed in. Same thing. Water and admixtures can be adjusted on site. You mix it in 30 revolutions and then do another check test. The issue with high air or high slump is that you can't take those materials back out. And most specifications do not allow adjustment. There are air detrainers that do exist. MDOT does not allow them, but on commercial and other jobs, we have seen it, or other jobs that use other admixtures that tend to foam up that are not air training admixtures, but they do they have a
Yeah.
surfactant in them and tend to foam up somewhat and add air to the concrete, even though it's not air that we want. There are air detrainers that will pop the bubbles. If you just like bacon grease left in the pan doesn't create a lot of bubbles when you try to scrub it with soap and water. Bacon grease is a detrainer in your kitchen sink, or any grease for that matter. Same type of, it's not a grease that we're putting in, but there are chemicals that exist, but not every specification allows it. There are viscosity modifiers that will tighten up the slump too. It doesn't take the water out. The water still exists in there, but it changes and kind of makes everything sticky. Those exist as well to reduce the slump if that is the concern, as long as you're not already over the water cement ratio. So, but again, not all specifications allow those to be used. So,
All right. There was one more question. You don't have to answer it right now. Maybe as we're going through it will kind of organically come up. But there was a question about some of the issues with new MDOT cement and some of the scale issues
yeah.
that people have been seeing. So maybe as we're going along, we can fit that in.
Yeah, we will. We need to do a whole webinar on that, Ingrid. So make note of that. So
Yes, I will make note of that one. All
I
right.
don't, we don't have enough time to really address that, but yes, that is, I kind of alluded to it earlier as far as unhydrated cement particles. If you don't have enough water on the surface, as well as potentially too much water on the surface. So
Yeah.
those are the main reasons why we have scaling, and we generally see lack of curing as the main cause of scaling. So
All right. We're caught up on
good.
questions.
Excellent. Let's get into strength test specimens. I may fly through some of these a little quicker since I belabored those other slides, which is fine. That's good stuff. And I love the questions. We'll talk about concrete test specimens. So, why do we make them, whether they're beams or cylinders? And actually, that's an interesting one. In the middle there, that's a splitting tensile test. Not very common, but a lot of researchers may use it for various reasons, and it's analogous to some other things. But we make test specimens because it's easy to do. We've always done it, kind of like the slump test. And it gives us as engineers, and I am one, a good sense of, okay, at least it's strong enough to resist the loads. And for pavements, slabs on grade, curb and gutter, concrete floors, sidewalks, drive approaches, driveways, when it's on an aggregate base or some sort of prepared subgrade, it's fully supported. Its strength is generally not a concern, even if you have low strength. Generally, that is slab on grade type of design will still work in most cases. Where where strength for me as an engineer is a concern is when we have it as a structural member in our bridge building, some where we're relying on or parking deck, those types of things where it's part of the structure. The strength is definitely more of a concern than in a slab on grade. So, but it is regardless used as the acceptance and payment in most situations. So when you have a low break, a low strength result, people get worried about we're not going to pay for it, or we're going to take a reduction, or let's wait and do some more, or do some more investigation. So it's just the way the specifications are written. Because the design is based on strength, then we're going to have acceptance based on strength as well. However, concrete cylinders or beams or whatever these samples or specimens that you're making, they are not the strength of the actual concrete in place. They represent the potential strength. Like we could be higher or lower than that, depending on a lot of different things. Primarily the curing condition of the actual cast in place structure versus the curing condition of the cylinder or beam in the field or in the lab or whatever. So they are analogous to what the strength is in the structure, but they don't mean that the structure is exactly that strength. And so it doesn't tell us that the concrete will necessarily perform over its intended design life. There's a lot of other factors that go into that on the design side, on the durability side, and things like that. But it is the basis on which the design is made and acceptance is done. The results of that might mean if it's low, remove and replace, or further testing is needed, or wait. Concrete continues to gain strength after the point at which we typically test the strength, which in compressive strength is 28 days. It still gains strength beyond that. And actually, we referenced earlier the switch to Type 1L cement. There are other states that have now switched to 56-day strengths. And so we are talking with some of our counterparts in other states where their DOTs or others have switched to that. And so we'll see if MDOT is interested in that or not. But a 56-day strength, because some of these cements are a little slower in gaining strength, and there is still some significant strength gain beyond 28 days. So, and there may be pay factors as a result of it, depending on, I think, on MDOT high quantity concrete paving jobs, they typically do a pay factor based on both strength and error. So strength is a portion of that. And we'll talk about these standardized test methods. All of these have a standard way of doing it. And I mentioned, our training and certification and all these different classes that we can do here at MCA and are required for a lot of folks on all these standard ASTM test methods. And certification if you want to actually get that as well. But they're standardized for a reason, because if you don't follow the test procedure, you just invented your own test method, and the results of that test method, if you don't follow the procedure, are not allowed to be compared with ones that do follow it. So there's a reason that everything is done the way it is. So yeah, typically field testing technicians will go out and prep their equipment, get their sample from the required truck or the desired truck, and then do all these different tests. In this one, we're going to talk about the strength test specimens. And I've seen research that's been done on the variability that can be introduced to the various different things. If you don't follow the rotting procedure, the tapping procedure, and the curing, and all these different things, how it typically negatively impacts your strength. Not, it doesn't usually add strength to the concrete. The more what we do to the concrete after it's been mixed and placed, typically does not add to the concrete strength. As far as timing on field tests, this is right in the specification for sampling. It's an ASTM specification. They have to get their sample, and they have to get at least multiple portions of their sample, depending on the type of mixer or vehicle that they're getting it from. But they have 15 minutes to get those individual portions of the sample, and then they have to combine and remix them, and then start their temperature, slump, and air within 5 minutes, and then start filling their test specimens within 15. So beams or cylinders in this case. Cylinder molds, there's a specification for those as well. They're always twice as tall as they are in diameter. So 6 by 12 being on the big side, 4 by 8 is that second one down. The third one there, 4 by 8, that's probably a 3 by 6, I think. And then there's probably a 2 by 4. Those other ones do exist, but are not very common. 4 by 8 and 6 by 12 being the most common. Oh, the size of the mold is based on the maximum size aggregate, the nominal max size that's in the mix. So if you have a mix that might have some 1.5 inch material, or I should say max, nominal max, yeah, might have some 1.5 inch size material in it, because 95 to 100% or 90 to 100% passes the 1.5 inch sieve. You could potentially have some 1.5 inch material. 1.5 times 3 is 4.5. You are not allowed to use 4 by 8 cylinders with material that might be of that size. So you have to go to the next size up, which is 6 by 12. Beam molds, you can be as small as 4 by 4 if you've got 1 inch diameter, but the standard is pretty much a 6 by 6. And then most of the brake machines have an 18-inch spacing in the supports on the bottom. And then the load is either in the middle or split into third points from the top. But the supports in the bottom are typically 18 inches. And the spec is that the beam itself has to be 1 inch longer than the center line of those supports below it. So 20 inches technically, if we could be perfectly to the right length, but most of them add an extra inch. So a 6 by 6 in cross section, and then 21 inches long is the concrete beam, the inside dimensions essentially of the beam mold. That's what's most common. Cylinders or beams should be labeled, identified. Most cylinder molds are single use, so they label the actual mold and then toss it when they're done because it's difficult to get out. You can reuse them a couple of times for the plastic molds, and some folks do that. But beam molds are typically reusable, whether they're metal or plastic. You can take the sides and the bottom apart and then clean them and reassemble it for next use. Cylinders and beams are very susceptible to that initial curing. Once the concrete's in them, consolidated and struck off, and a cap is put on, or a curing has been put on, sprayed on the beams, or a cap on the cylinder molds, they're not brought back to the lab right away. They are allowed to be brought back to the lab only 8 hours after they've been had set, essentially had final set, which usually happens within the first 8 hours typically of a typical concrete mix. So usually the next day they can be brought back to the lab as long as the lab's within 4 hours of where the project site is. And then, because 4 hours is the max transportation time. And then they are not allowed to be left in the field longer than 48 hours. So typically they're left in the field 24 to 48, but usually picked up the next day or less than 2 days later. But that initial curing in the field, they have to be moved to there within 15 minutes of when the cylinders have been fabricated, or the caps put on, if they're cylinders in this case. Then they're moved to that initial location, and then they're allowed to sit and set and undergo that the hardening process, at least the beginning of it. And that has a lot of requirements for that initial curing. In wintertime, it may mean that you have to provide artificial heat And there are coolers for these cylinders or beams that you can put them in that actually provide artificial heat, or you should put them in the same area as long as it's 60 to 80 degrees, because that is the requirement for them, that they be in the field maintained between 60 and 80. So you need to have assurance that that is what is occurring. Again, beams typically have just curing compound sprayed on the top or wet burlap pulled over top for curing, and the cylinders typically have a cap put on, but they do need to be picked up and brought back to the lab. Standard mixes, like I said, 6,000 psi and below as their design strength, need to be between 60 and 80 in the field. For high strength concrete mixtures, not very common for MDOT work, but for commercial work, high rise buildings, things like that. A lot of times we'll see some high strength mixtures being used. I've heard of mixes in high rises up to 12,000 psi. So in that case, that 20-degree range shrinks to a 10-degree range, 68 to 78, if you do have high strength concrete, because it's way more susceptible to that initial curing condition. So min-max thermometers are the only way to prove that your specimens in the field were maintained between 60 and 80 in that initial curing prior to being brought back to the lab and undergoing standard curing for the remainder. And so there's lots of different ways to keep them between 60 and 80. Most use a cooler, which is great because that can help at least contain or reduce the influence of the ambient air temperature as far as if it gets below 60 or above 80. However, in the winter, it's not a bad thing because the concrete cylinders are actually giving off heat, and so you don't need to usually supply external heat if they're in a cooler. But in the summer, that heat is kept inside that cooler, and that can oftentimes be a bad thing because then they get way above 80 degrees, and that cooler becomes a heater, essentially baking those cylinders. So I've heard of technicians taking empty cylinder molds and filling them with cold water, filling up the cooler with cold water, from the ready mix truck, the hose and the tank on his truck, on the driver's truck. Or I've heard of some even in really hot weather filling some of those empty cylinder molds with ice and filled with water so that the ice will melt and the water itself also will act as a heat sink to pull all that heat that's being generated by those cylinders, and we'll pull that heat off and we'll go into the water. You don't want them to freeze. Obviously, you want to protect them. They can't be below 60. And because if the concrete's allowed to freeze inside those cylinders prior to them achieving, a significant amount of strength, that'll cause damage, and you'll get low breaks, and then you'll think, oh, they gave us a bad mix. Our concrete, is bad. It's going to fall down. It's going to have cracks. But was it just the cylinder, or was it the actual in-place concrete that is the issue? Transportation, as I mentioned, they got to be in the field for 8 hours until final set, and before 48 hours, they need to go back to the lab, and they need to be 4 hours within 4 hours. So there's different devices that can be used, racks. You don't want them rolling around the bed of a pickup, banging around, especially depending on your driving habits, because that can pre-crack them and damage them, so that when they're actually loaded and tested at age 28 days, that they might have some damage from that. So, and once they're back in the lab, they're typically demolded and then put either in a lime water tank, and it has to have a certain amount of lime in it per the specification so that it doesn't leach it out of the concrete, or they're in a 100% moist cure room like you see in the bottom photo. Regardless, they're kept 73 and a half plus or minus 3.5 degrees Fahrenheit, so 70 to 77 as far as the temperature when they are in the lab. And then loaded at the appropriate age, and then the strength recorded as a result of that. But there's actually some measurement that needs to be done to ensure that it's not 6.1 inches instead of 6, or it's not 4.05 inches instead of 4. So those things need to be done per the test method that's being used. There are a lot of different breakers out there as far as compression machines and what we see here, which are the beam machines. The one on the left, we have one of those. That's a center point loading machine. versus the one on the right. That load in the middle, you can see is split into two. There's two rollers underneath that plate, and those rollers are located at the third point. So they're 6 inches apart, and they're 6 inches from the supports on the bottom, which are at 18-inch spacing. And that gives a third point loading. There's actually two different test methods, two different ASTMs, and they yield two different numbers given the exact same beam. So you don't want to interchange those results. And in fact, ASTM is doing away with the center point test method altogether. It's going to be a historical retired test method, and they're moving everything to third point. But all of MDOT's tables in their Division 1 of their spec book and Division 6 and everywhere else on concrete opening to traffic strengths are all based on the center point machine. So that's something we're going to be talking with them probably in the next spec book revision, which is probably in the next, it's probably 3 to 4 years. So be aware of that. But we have to, the technician doing the braking has to measure, because even a tenth of an inch or a couple hundredths of an inch in cases can affect the calculation of that. So we have to be very accurate. It's not just a 4-inch diameter, and assuming it's 4.00000, we actually have to measure it to very high accuracy in order to make sure that calculation is accurate from what the load is over the area to get the PSI, the actual strength. So that all has to be, and then the reports are typically formatted. The companies typically have a standard format that they have for their system or their company or their machine. And those are provided then to the clients or whoever is paying for the testing, obviously. Same thing with beams. They have the same type of thing as far as measurement to ensure we have accurate calculations. May need surface corrections if that cylinder, or in some cases beams, is not entirely accurate as far as how perpendicular it is and of the surface compared to the sides, the roughness or voids in the surface or the sides and things like that. So different capping methods, the gypsum, sulfur, or we use neoprene pads. It's probably the most common with a metal restraining ring, like you see pictured in the middle. That's what most folks use. But in some cases, you do have to resort to the capping or grinding options. There are grinding machines out there that can automatically and accurately do these the surfaces so that we have perfect perpendicularity and everything else. So, and then there's a whole test method, obviously. Oh, you had a question, Ingrid.
Yeah, got a question about the placement of concrete when, everything is cured properly by the testing technician and kept within the right temperature range. But the in-place concrete is under conditions that might be below freezing. Is this when maybe you should do some post placement testing?
Yes.
Or, okay.
Yep, that comes down to proper care and protection of the actual work, not just the test specimens. And that obviously is on beholden to the contractor to protect their work. And so, like MDOT specifications have information in there on what you need to do based on what you're placing, bridge decks and pavements and curb, whatever. And so, below freezing, do this. And we have some a guide on that as well. Like when can we just use plastic? Do we need to use blankets? How cold is it getting? So what protection measures do we need? It depends on, how thick it is and how much heat it's giving off and the mix design and all these different things. But it also comes down to inspection, ensuring that the contractor is doing that and holding their feet to the fire and making sure that they're doing what it says in the specification. Because yeah, we've looked at stuff in the past where the surface froze and then came off, within weeks, in fact, because it wasn't just freeze thaw over time. It was that initial freeze that caused that scaling or whatever it is to happen. So yeah, there's definitely a lot of care that needs to be taken to protect the concrete in service, not just the test specimens. But if you're protecting the concrete in service and not the test specimens, you can't rely on those. But then if you're protecting the cylinders and test specimens, but not properly protecting the concrete, you'll definitely have issues with that as well.
All right. Just an announcement for folks. I did put the certificate of attendance survey into the Zoom chat. We are recording this, so if we go long and you have to jump off, you can always refer back to whatever you missed. But that is in the Zoom chat right now. So, all right, I think we're all caught up on questions,
Cool.
so you can keep
Excellent.
going.
Yep, just got a few more minutes here, a few more slides, and then we'll be done. But I was saying about there is a obviously standard test method in order to properly break what we're pictured here is a cylinder for all that, and we do classes and certification on all that, and a lot of specifications don't require the certification, but a lot of labs like at least one or two folks that are doing this all the time to have that or be supervised by someone who has that certification. ACI is talking about splitting it so that there is what we're affectionately referring to as a cylinder buster certified technician, and all they're certified or trained at least and have been certified to do is to take the cylinders, put them in the machine, and push the button and record the results. I know I'm dumbing it down somewhat, but that's essentially the production line worker. That's all they're doing, and they're supervised by someone who has the full certification. There is talk of that. ACI moves slowly, so it may be a while before we start implementing that because we haven't heard that it's been approved at ACI yet. But we would offer that here locally as well in Lansing once that is done. Beams, this done a lot in the field for, like I said, for opening to traffic. You do not require a certification to do it. It's pretty much information only, right? Whether you can open to traffic or not, there's no payment typically based on it unless it's a concrete patch job. In which case, if it does meet opening to traffic strength, then it meets the required strength for the joint repair job or longitudinal full depth repair or transverse full depth repairs. So but this is done a lot as far as getting those opening to traffic numbers as well. But there's a whole specification on properly doing that. And Michigan MDOT, I believe, has an MTM on it as well, but there is an ASTM on it as well that is throughout the industry. But then applying the load depends on if you're doing a beam test or a cylinder test, and the ones that are computerized accurately, bring up the load within the required time frame. They don't overload, and it's a continuous. The computerized ones are nice, especially the ones that have a pump integrated to it because it's consistent and constant versus the hand pump. You're actually, loading and then not loading every time you retract the handle of a pump. So there's some debate as to whether a hand pump is continuous or not. Yeah, question.
Yeah, which elements in a concrete mixture should be taken into account when using a Schmidt hammer, and how do those elements affect the output of the test?
Yeah. Schmidt hammer or rebound hammer is the surface strength of a concrete slab or flatwork. It's very dependent on the finishing techniques. We typically see it used where, yeah, there's been a strength concern on some flat work or on a floor, and it's usually because of some other reason why the cylinders or whatever broke low, and then we go to the in-place slab and we say, yeah, but it's rebounding to a 5, and that's analogous to a 4,000 psi or whatever. However, it's very susceptible to the finishing operation of the surface. Did you get on it? Was it a floor slab that you got on it with a ride-on power trowel? And put a lot of finishing effort into that floor slab and burn the surface and really densified it through that finishing, which is fine. It's not Aaron trained, but that makes it a very strong surface. Or is it exterior flat work where you want to touch it as little as possible and just strike off and bull float and texture, room texture or whatever, and then you didn't do a lot of finishing to that surface. It's the exact same mix with different finishing levels of finishing can have a different rebound hammer or Schmidt hammer number or result. So
Okay,
it's
got
kind
it.
of it's a rule of thumb type of thing. All right, we teach this in our class as far as the type of break that's noted then, but I'll just go real quickly through that. The type 2 is common if we're using the rubber pads, which is again the most common, the neoprene pads and the steel restraining rings. Type 3 is if there's no friction at all between the concrete cylinder and the loading plates. Type 1 is rare. It's very uncommon, but most lab reports that you get when you look into the break results, they'll note which type occurred on that particular break, essentially. But no, types 4, 5, and 6, typically something is wrong. There's something weird going on with the concrete. that and um, type 5 might be that you stop the test early if it's just a little corner break off the side. Type 6, maybe a capping issue. So, and then flexural breaks, middle third is most common. You see that is a third point test where it takes the top load and splits it along that plate into the two loads where the rollers are to find the weakest point wherever it is in that middle third. A center point test forces it to crack right under the center point loading, um, which typically also then results in a higher strength and sometimes more variable strength because it could be the strongest spot, it could be the weakest spot. So a little more variable with center point. So that's why middle third you typically get a lower result. It fails whatever the weakest point is in that middle third of the distance of that beam. So. And then there's calculations to figure that out. We're not going to get into that. Nobody wants to do math on their lunch break while sitting through a webinar. And then the final report is produced. And like I said, most labs have a standardized report that you look at and has those all that information. So if you dig into those reports, you can learn a lot of things. But most people are just like, all right, did it meet strength? Yes or no? Okay, move on, which is really all that needs to happen. So I mentioned we do certification classes. We do most of the ones listed here. Obviously, the field testing level 1 is kind of the main one that we do most often, but we do offer all these at some point throughout the year. Interested in that, let me know. And then as labs, a lot of these companies that do these testing, they can go after these accreditation. At the minimum, the ones that do MDOT work have to participate, their machines, the compression machines have to participate in our round robin testing protocol that we do typically every fall. And so a lot of you, if you know that, you've probably, heard of that in the past, maybe. But there are other accreditations and things that the folks like Corps of Engineer requires certain things. If you want to be an AASHTO, Emerald accredited lab, there's also the CCRL accreditation procedure. So a lot of labs go after that because certain job types require that the lab have that accreditation. So. Oh, moving on, we got some logos popping up here. Other certification agencies, I mentioned ACI. We do a lot of their ones here in Michigan, NRMCA, we do those, but there's others out there. All right, summarizing here. Test specimens that are made poorly, cured improperly, or damaged in the field or during transport, that's the strength of that cylinder. That's not necessarily the strength of the concrete in the structure. So if you get a low break result, it's just a trigger to be like, hey, let's figure out what the problem is. Is it this cylinder? Was that the problem? Or should we go investigate the actual concrete that was placed in the field and look at that? So, and to summarize, I'm 1 minute over, but we'll quickly summarize the fresh concrete tests. That's typically where we have a lot of opportunity for QC quality control as well as process control of our whole process. And that should be a feedback loop and two-way communication so that everybody's talking and that the fresh test results are communicated from QC to QA. And then QA can say, oh, well, we did some fresh test results and you're giving us results on time. So therefore, these are ours just for information only. QC tests are what we use for process control and adjustments, but informational tests and the flow of information is really what's key to partner together. So that's how we build quality concrete is partnering and communication with all those test results. The strength tests are typically what we use for acceptance and payment in concrete, but that does not mean we'll always get durability because we just got strength. It doesn't always come along with it. But also the converse, low strength does not mean that we have bad concrete necessarily. It just means we need to look at why we might have low strength test results. So, are there any questions before folks want to be done with their lunch break looking at me talking about?
There was a question. Someone asked, they may have missed it, but are the classes that you were mentioning, are those virtual or are they all in person?
The certification classes are all in person because that is a certification. We required the person to be there to make sure they have the right ID that matches, them. That's a requirement of ACI, not of us. We're a local group that is beholden to what the certification body has for their rules. So that is all in person. And many of those have a performance or demonstration that they can do these tests because it's literally these you have to test the material, and that has to be in person. We have not gone to where there's a camera, and going on site, and we can do it all like this, like we're doing right now with all these people. Um, and yeah, so all that as far as certification, that's all in person. For our training, and we do concrete contractor 101 and 201. We implemented that this year. And we're happy to do these lunch and learns and other things. A lot of that can be done virtually, and with our renovation here of our classroom, we're gonna hopefully add that capability.
Yes, and I will put, this is a perfect segue. I'll put the survey link in there. You have the opportunity to request topics that you might want to hear about. So if there's a specific concrete topic that you want to hear about, we'll try and make a lunch and learn about that. So make sure that you fill that out if you're trying to get that certificate of attendance. I do want to mention the certificates of attendance for all three of this series will go out after the last class, which is next Wednesday. Another lunch and learn. So try and be patient with us if you don't get it immediately. We'll also send out the slides at the same time when you get those. And I did have a couple of questions. I will be posting the YouTube video. So we are doing this as a recording. I'll post that here later this afternoon before I leave the office. So are there other concrete related questions before I stop the recording? Anybody else have anything else? Steve, thank you so much for this. This was
You bet.
excellent. I think folks got a lot of great information. All right,
Happy to
I'm
do
gonna
it.